Good morning, everybody. Today, I'm going to share with you this work. It's kind of a nice follow-up on the keynote where we're already talking about plastic hinge bridging and seismic resilience. And this one's about ECC, or the bendable concrete. But it's not a traditional ECC because it's a high-strength engineered cementitious composite with nanosilica incorporated, and we are going to study its mechanical performance as well as its autogenous self-healing behavior. And my collaborators are Dr. Zigang Zhang, and also Zhipeng Li, and Dr. Jialuo He. All right, so first of all, I'd like to acknowledge the sponsors, the work sponsored by Tridely, as well as Dr. Zhang was sponsored by his grant from China. And the work was actually a few weeks ago published in Cement Concrete Composites. Now, to begin with, what is ECC? Again, we know it's called also a nickname bendable concrete. Basically, it's a premeditated matrix of fiber and cementitious material and the interface in between. So it's carefully designed so that it will have certain behavior, such as high ductility. In other words, quite different than the conventional concrete, which is very brittle inherently. So the design was based on micro mechanics theory, and the study has been, this line of research has been going on since the 1990s. So this type of material is features high ductility and strain hardening behavior. So the also known as strain hardening concrete. And also you have this so-called saturated multiple macro cracking behavior and autogenous healing, because usually the width of the cracks are less than 100 microns. Again, back to the human hair diameter is roughly 80 microns. So instead of having a large wide crack, you have multiple hairline cracks. So it's easier when you have the material going through wet-dry cycling, because of the combination CO2 from air reacts with the pore solution in the material and deposit calcite and heals itself. Now, again, in recent years, there's a desire to go for higher strength ECC because traditional ECC is not that high strength. So we're kind of converging with UHPC, even though not reaching the level of UHPC, depending on how you do it. There's some research trying to kind of combine the benefits of UHPC and ECC, but that's not the emphasis here. Here, we're trying to get to better or higher strength ECC. So what you see in very recent years, there are a few studies, sometimes you can get up to 210 megapascal. How they do it usually, traditional ECC is using PVA fiber, or also known as polyvinyl alcohol fiber. Now here we're using a high strength PE fiber or polyethylene fiber. And this kind of fiber can help improve the strength because the fibers are different. The challenge though is a PE fiber is not hydrophilic. So they don't bond well with the cementitious matrix. So there's what happens next, then earlier I was talking about the traditional ECC, your maximum crack width will be around 100 microns. For PE fibers, you end up, PE ECC, you end up with 150 microns. So in that case, it's harder for them to heal itself when it's cracked. So in order to improve the crack width control and also enable better self-healing, we need some creative solutions. So again, nanotechnology, we talked about this yesterday, nanomaterials are not simply nanofillers, they actually work as almost catalysts, because they offer nucleation sites for the cement clinker to hydrate, and also they regulate the hydration process, so you end up with more, better density CSH gel. All of these effects contribute to better, denser microstructure and better mechanical performance and better durability. Among all the nanomaterials, one relatively affordable material is nanosilica. And in addition to all the previous mechanisms, they also feature really high surface area as well as pozzolanic reactivity. In other words, they can react with pozzolandite in the cement hydrates to form additional CSH gel, so make the concrete even denser and stronger. And this has been, I mean, the use of nanosilica has been explored in fiber reinforced concrete, including ECC. Then why the need for this work, I guess? The studies out there typically did not look at the high strength ECC or the PE ECC. So our hypothesis is that by admixing nanosilica at no more than 1% by weight of the cement binder, cementitious binder, we should be able to make the ECC matrix denser, while at the same time improving the bond between the PE fiber and the matrix. Like I mentioned earlier, PE fiber is hydrophobic. They don't bond well with the matrix. Anyway, we'll talk about this a little bit, just like the SMA, we were talking about the bonding earlier. Sometimes actually, it's a tricky balancing act, how strong you want to make the matrix versus the bond. We'll get into that. But the hypothesis is that the nanosilica will actually do the magic and help us achieve that balancing act. So the other hypothesis is sort of like, okay, with the nanosilica, we'll be able to sort of close the gap. Instead of 150 microns, we can make it much narrower so that it will facilitate the autogenous self-healing. Now, the experimental design, again, this is very much more like a proof of concept. In other words, we're not trying to optimize the strength. Here, we're just trying to test the hypothesis, whether or not the nanosilica can do the job. So you end up with two mixed designs. The group one is M1 is, you can see this a little bit of ash, but group two, however, has a lot more fly ash. So it's a high volume fly ash binder because you have more fly ash than cement. And unintendedly, you'll find the self-healing behavior is much better. Not planned. We were just trying to use a greener binder, more sustainable binder. But in the end, actually, this one works really well in terms of self-healing. One thing you'll see is the reason you'll end up with really high strength, usually, actually, you will see 28-day compressed strength more than 75 megapascal because the water binder ratio is relatively low, 0.204. And the PE fiber was added at 2% by volume. And this is a PE fiber, again, finer than your hair because diameter is 26 microns and the length is 12 millimeter. Again, if we were to optimize the performance, we can play with the aspect ratio of the fibers. Like longer fibers may give you better results. Now, you can see the size gradation of some of these solid constituents like the cement, the ash, the silica fume, the sand. But actually on that chart, there's nowhere you can find the nanosilica because that would be at the very left side because we're talking about, less than 100 nanometer, which is less than 0.1 micron. So it's the very end of that curve. So we used an uniaxial tension test to evaluate the tensile performance of the PECC. One thing we found is, which is kind of consistent with our understanding, is the nanosilica helped promote the hydration of the cement particles. If you see the left-hand side, as you increase the dosage of nanosilica from 0% to 1% by weight of cement, or weight of binder, I should say, then your non-evaporable water content increases. That's basically the bond water, which is an indicator of the degree of hydration or degree of polymerization of the CSH gel. But you will see also with the M1 series, which has less ash, you're seeing a more increase, but with a lot more flash or the high volume flash binder, you're seeing less because there's not enough polyandrite to react with the nanosilica. And also through the TGA or thermogravimetric analysis, you can identify how much polyandrite or we also call it CH phase is in there, which is the peak around 380 to 425 degrees. That's the peak. The area and the peak kind of indicate how much polyandrite you have. So when you take that number and plot over here at the bottom, you'll see as you increase the nanosilica, you're seeing a significant decrease in the polyandrite because again, they reacted with the nanosilica to form additional CSH gel. And again, comparing with M1 series, you're seeing less prolonged because you start with a high volume flash binder, you don't have as much cement. Now, in general, the good news is that the nanosilica did benefit the mechanical performance. For instance, at 28 days, the 1% nanosilica improved the compressor strength by about 16% and 8% respectively. So it's not very impressive, honestly, because in most traditional concrete with 1% nanosilica, you'll be seeing something around 20% improvement. So because this is a specialty concrete, so we're not surprised. And overall, you can see these 28-day strength is pretty good, better than higher than 75 megapascal. And also, by the time you reach 60 days and 90 days, you basically don't see significant difference between the two, M1 and M2. What that means, you can get away with M2 if you're only looking at long-term performance or long-term strength, which has 1/3 less cement, so it's a lot greener binder. As I will show you later, and so also another unintended benefit was the self-healing was much better in the case of high volume flash. Now, again, this is not your traditional concrete. That's why you're seeing this kind of strain hardening behavior. The reference M1 is the one without any nanosilica, and then 0.5% nanosilica, 1% nanosilica. You see this kind of tensile behavior. And then, but from the M1, the reference one, we can see that, well, it's not a very good ECC because you're not achieving really good ductility, because in that case, basically indicates you either need a weaker matrix or stronger bond between the fiber and the matrix. So again, it's a balancing act. So in terms of stronger bond, you can see once you add nanosilica, you are achieving stronger bond. Therefore, you're getting better ductility and better tensile behavior. Or you can use a weaker matrix. In the case of high volume flash, you have a weaker matrix, you're achieving better ductility. For instance, especially this one, you can achieve 5% or 6% ductility, which is very bendable concrete. So here's a lot of quantitative information derived from those curves, the tensile curves, stress strength curves. So you can see that we derive the first cracking strength, which is very important. Usually you don't want the first crack to occur until it's totally necessary. And then you have the tensile strength, the strain capacity, and modulus. You want all these parameters to be high. Now, just one example, when you add 1% nanosilica for the M1 series, you're seeing this kind of improvement, 23%, 24%, 58%, and 17%. So it's not bad. 1% nanosilica, the cost increase is very minimal. Nowadays, nanosilica is very affordable. So what about the fracture properties? When we look at, again, like I mentioned, the high first crack strength is desirable, but along with that, when you increase the first cracking strength, you're also increasing this so-called high fracture toughness, or the KM. And the KM is actually closely correlated with this crack tip toughness, or the J tip. And as I will show you later, actually, in order to enable saturated micro cracking behavior, you don't want too high a J tip. So you're kind of, again, a balance act. You don't want to make the matrix too strong. But because of nanosilica, you actually already made the matrix stronger. So this chart is a little bit confusing because you start from the middle, you go to the left, is M1 series. As you increase the nanosilica, you're increasing the J tip, the fracture toughness, as the M2 is on the other side. Again, they're showing the same trend. Now, because you improve the matrix, you also hope that it also improve the bond. So that, again, a balancing act. It did improve the bond. The presence of nanosilica, you look under the microscope, for instance, without nanosilica, you're seeing more coarser, more porous microstructure. On the right-hand side, when you add 1% nanosilica, you're seeing denser microstructure. This translates to a higher friction bond between the fiber and the matrix, which is called tau 0. Okay. So the idea is that the strain capacity improvement was due to the denser microstructure and the better bond. Anyway, you're seeing this kind of behavior, again, micro cracks instead of wider cracks. And when we quantify it, what's interesting is you're seeing, like I said, M2 series 1%, the micro cracks average only 23 microns. So you see that blue dotted distribution, the Gaussian distribution, it's shifted way to narrower range. That helps the self-healing. So we're seeing this kind of better behavior as ECC. Again, if we consider the hardening, hardening index, which is the JB apostrophe divided by J tip, that means not only we improve the fracture toughness, the J tip, but also we further improve the other one, the JB apostrophe, because that's the amount of complementary energy you need to induce additional cracking when after the first crack is formed. So it's all going the right direction. And we did see this kind of behavior. Again, the high volume flash one give you much better self-healing. And to conclude, basically we're achieving a high strength ECC with, sometimes even a high volume flash concrete. And they were able to make the matrix denser, improve the bond. And one thing I should mention is that in addition to enhancing the mechanical performance, you also have more cracks, narrow cracks, and better self-healing behavior. And heating products were actually different when we actually characterized the high volume flash one, because the cracks were narrower, the product was mostly CSH. But the wider cracks, the product was mostly calcite. So we're seeing this kind of behavior. And what really intrigued me, honestly, is this one, the high volume flash one, because you are achieving a grainer binder, high strength ECC, and really beautiful self-healing behavior. With that, I welcome your questions. Thank you. Yeah. Right. Yeah. In this case, we use the Class C flash, which, I would say Class C in the country probably is about 15% of the ash out there. Yeah, more commonly people use Class F. However, there's a benefit of using Class C because Class C traditionally is really difficult to use. So, so if we find a good, outlet for it, it's nice. Yeah. Yeah.
Very interesting presentation. Just a curiosity regarding the fracture, and so use some terminology that sounds like linear elastic fracture. And so we're wondering really how you measure the fracture energy. So they mentioned usually when you apply first the matrix cracks,
right?
You have an energy for the matrix, then you have that long tail fracture. But that's another factor there. So how do you compute that?
Right. That's a good question. First, I have to acknowledge I'm a chemist by training, so fracture mechanics is like here. So so my postdoc probably will be able to answer that question better. So I'll get back to you on that. I don't want to pretend I'm the expert in fracture mechanics. Yeah.
Autogenous self-healing behavior is very interesting. So you mentioned that you have 30 5-life cycles.
Yes.
So what is the duration? How long?
Right. I think, well, I have to go back to the paper, but I think it was every 12 hours. Yeah, so it says, yeah, 1 day. Yeah.
So the 30 5-life cycle, 15 days.
I would say 30 days.